这是我要播的。懂的，但是它也是一个特哦，是我这边写签了好听的。但是你要看地方版是不一样的。你是两个备注吗？ 老师开始。不要那个圆圈，你要理解那个圆圈是，就是 x 等于 y 的对 sin，你要理解。先想好了这样给我想想，把事情自然开始，也是也是。先讲10个完整，然后再去改，很怕点先把那个。但是我觉得你编对了啊。对，我方向你自己去。我们在这里。我整方很好的。我先讲说，首先我讲这样，小一点， 喂，就找得到吧？找不到的话就再测。而且你也没有那等兵都在这里写的。这边，要不然你就是这个 threshold 就是你的范围，一定要有一个东西在那个点上面的，那意思在那条线上面有一个噪音的东西，但是不一定的，可能你的噪音是低，所以你是说把 OK，其实就是高过这个号码直接有出来。啊，还是谁换出来？对，加减啊，加，多啊，全部写过去了。找不到，他们有一本那个，我真的找不到，你可以留取那个。说他要结合起来的，要结合起来，除非你，除非你，我的 point 是这样结合起来，然后你分开的话， 你可以，I mean，但是你要解释说，说在这个你是在什么情况下有？哦，在 Seng 里面，那啊，不然的话就啊，后面啊，因为这个，我觉得状态，那个我在往聊边，如果他那个那个时还哎，哦，我说他在你，这个解决，那个解决是我关，可以在我们是做手术，对，反正效率还比较好，嗯，是其中一个是一个，这样的话你5.3931，是不是5点进来？是是用数张的，你不然先不是，不然先给这样。没有，你看给我，跟我们有任何关系？哦，好，这里这个是要问题题。啊，哎，你们写要不就简单的，没有一个没有版本。当然没问题，比如说我们这个 W 这样，能写一个点八讲无人问题的讨论什么话？来，一个题就是对讨论问题的。
写这样写什么可能是
很短话是吧？
那假如这个问题我们要，然后第四问就是
我的是好处，我会说
他这个没有讲到，
大家一定要
这个我们删掉了吗？我们没有这个吗？我那个有
哇，这一关这东西挺难找。结果你就有追求，这东西不能说一个每个时代这个园区，因为这点在硬件哪里的，在那个每年这边吧，就在这边，就是这条边。对，这条线它发进去，但是我觉得很新啊。那个这个。那 radius 的用，这个用这个这个属于讲的。这样，我们拿一个很高的。一个兴趣啊，很正常。对，因为我们知道我这个电脑是是就是
听不到这个，
它也是有，马上决定就是这学习，
这个时候听不到这个，
几岁？
对啊，
这样子了解。很想象这个。
总共几年？
总共是3
讲什么几个？
讲决定这个圆圈，这个当然这个圆圈最小的也是我的点。为啥呢？去分讲这个是二减三，一个二减三。啊，因为小篮球，然后你还有中间就是个圆。外面那个才把你放在这个，这个是很好的朋友在。 好玩一点到200的话，你这边拿到
现搞我们节目一切
就人你想的一些。
对对，你这种很像
我的话 A 零啊，没有，
他们
正在连接，连接话筒，已解锁，请启动话筒。
Okay, let's start first. I'm not sure if we can finish earlier today. If we finish earlier today, then we can continue to ask feedback on your report, or during the break you also can ask. Or if really don't have enough time, we can extend half an hour after 12 p.m. Okay, so let's finish up this week's content. Okay, let's finish up this week. This semester content. So one thing I promised to show you last time, right? So are you familiar with this theorem in your ODE or not? Is this your textbook you are using? The textbook you're using. You know what this theorem is saying about? You 看过吗？这个 theorem，这 theorem 在讲什么？啊 ，phi(x) 的存在 ，phi(xy) 的存在 ，phi(xy) 的存在 ，phi(xy) 的存在 ，phi 是什么来的？第二次 OD 课本 ，phi(xy) 是什么东西来的？哦，potential equation。OK， right. Potential equation good. 我们不是也有 potential 吗 ？Conservative vector field, gradient of a potential. OK， 有什么关系啊？看得到 vector field 在这边吗？有没有看到 vector field？ 你应该要看到 vector field 在这里。Okay, so how about this line here? If you can here rewrite this line here, the condition of this line. Yeah, I can rewrite it as mxy plus nxy times dy dx equals 0. Okay, and then if I do some illegal thing, maybe we can separate the variable. Do this. To 0. Okay, but what is this? Some function dx, some function dy. Can write it as a force time the change in distance. And then I can do, I can do integral on this thing here. And what's this integral here? You are integrate over a 0. So you get a 0. And I can do this integral on a loop, right? So I check on all loops, the work done is 0. Meaning what? Meaning what? meaning the vector field defined by this M and this N is conservative. Okay, is conservative. Conservative means what? I can write this vector field as what? As a gradient of a scalar field. Okay, so in this theorem here, where is your scalar field? The scalar field is this phi here. Phi differentiate with respect to x, you get n. Phi differentiate with respect to y, you get n. Because I can write f as a gradient of phi. Can follow? Can follow? follow? Yeah, 别听吧。follow 还记得吗？忘记就你纯粹忘记那个铁人吧。Okay, I just try and net for you. 没有什么 content 在这边 ，content 是我们讲过的东西。这些 fact 你要记住一下。有问题吗？Yeah. Okay. Yeah. Okay. So, what you really do is doing on the vector field. Okay. So this is a connection with exact differential equation theorem with vector calculus. Okay. All right. Let's continue our parameterized surface. So let's recall. Parameterized surface. Okay, let's recall using an example. Using an example. So do you still remember what the spherical coordinate is? What's the spherical coordinate? X equals to x, y, z. How do you set your x, y, z? X equals to rho cosine theta phi theta phi theta, then sine phi. Oh, you put the sign at the back. Okay, I prefer to put it at the front. Okay, and then y equals to rho cos phi down, and then oh, sorry, thank you, sine phi, and lastly you get rho sine cos phi. Okay, so what this spherical coordinate give you is a bunch of sphere. Okay, a bunch of sphere. Where's the center of the sphere? Where's the center of the sphere? At the origin. Okay, so I give you a bunch of a sphere. Okay, different sphere with different radius. So if you take rho equals to 1, then what you get is a sphere with radius 1. Here, a sphere with radius 1. Okay, so if we take rho equals to 1, then we will get a sphere with radius 1. Okay. Then this is so this sphere centered at origin is okay with radius 1 is a parameterized surface. So how should you think about this parameterized surface? Last time I give you an idea, right? Every surface should come from a flat surface. flat plane. Okay. But what's this flat plane come from? 等下拿到这个 sphere. Okay. How many variables that determine this sphere? Can you recognize here? How many variables? 2, right? Okay, so there are 2 variables to determine here. So your phi have to take from where to where? From 0 to 2 pi. And then your theta going from, your pi is just going 0 from 2 pi. And then theta from 0 to 2 pi. Still remember where this phi counting from? This phi should come from the positive z-axis. Okay. And then your theta count on the xy. On the xy plane in particular, you start from the positive x-axis. Okay. Don't put this y. There's not y. It's just a direction. Okay, should I put the y up? Yeah, maybe I put the y up. And then you have this angle theta here. Okay, and then your phi, maybe you have another angle for your phi. Any question? 原题吗? If you think there's something weird, please ask. Yeah. 有问题就问啊。没有问题就我们可以继续。So what's the plane? What's the flat surface that build out this sphere here? So you can form these theta phi plane. Okay, theta phi plane. So if I put theta here and then phi here, then I just take theta from 0 to 2 pi, and then I take phi from 0 to pi, and this rectangle here will help me build this sphere. Okay. Is it clear? Yeah. So you can see that in spherical coordinate here, right? Radius will change. Okay, radius will change. But once we fix the radius, we just get a single sphere. So parameterized surface involve 2 variables. Parameterized curve, how many variables? How many variables? 1. Okay, 1 variable. So you can see that this surface here, we have r phi theta. Okay, going to x, y, z. So this is a map from R2 to R3. Okay, and then curve is from R to R3. So these two theories parallel. You see a parallel thing. So in what? In parameterized curve, we also have we find the tangent vector. Okay. In parameterized surface, we can find the tangent plane. Okay, we can find tangent plane. So one thing you need to memorize is okay, we call these curve surface manifold. So these manifold, right, have the same dimension with the tangent space. Okay, if you have curve, the tangent space for your curve is tangent line. If you have surface, your tangent space of your surface is a tangent plane. Okay, it's the same dimension. Okay. Okay, so how to get the tangent plane? Okay. Wait, suppose okay, so let's suppose there's a parametric surface. Okay. as given by RUV, okay, which is XUV plus YUV plus ZUV. Okay, so in your mind, you should think about the example just now. What do we have just now? R phi, R theta phi equals to sine phi cos theta plus sine phi sine theta plus z. What's z there? Cos phi. Okay, so hit the sphere example in your mind just now. Once you have this, you can form two things. So you can form two tangent vector. Okay, you can form two tangent vector. So what's this two tangent vector here? So you can differentiate r with respect to u, differentiate r with respect to v. Okay, but how do you differentiate it? So you just do partial derivative on every component. Okay, so we kind of combine what we learned for partial derivative and vector function. And so on. Okay. So what's the tangent plane? So how do we define tangent plane? Definition. Plane on the surface. The surface X is the plane that contain these two tangent vector here. Okay. You might wonder. What do you wonder? You might wonder. Is this two tangent vector enough to define this plane? Enough to define this plane? You should think back to the partial derivative chapter there. So what's the two important partial derivative you learn? Which two direction you learn? In x and y. Okay, del x and del over del y. Okay, and then that two partial derivative, you can build all the directional derivative. Do you remember? You can take the dot product of your gradient with your any direction you want to look at. So let me recall for you. So recall directional derivative. Okay, so if you want to like look at a certain direction, right, u of f, what do? You partial differentiate f with respect to x and partial differentiate f with respect to y, and you dot it with the direction you are looking at. Okay, so all direction you can get from these two kind of linear independent. Okay. So same as u and v. U and v will play the role of x and y here, because you are two linearly independent coordinate. Okay. Yeah. Okay. Any question? Okay, so what's the next thing we learn after learning parameterized curves? We try to compute the arc length, right? Okay, but for surface, so if you have a surface, okay, look at the surface here. You can see that this surface will span out an area， it is an area， 另外一个 area， 你可以放你的 juice coffee 在上面。如果没有 area， 是不是放不了 juice coffee 啊？ Okay. So they spend out an area. So how do you compute area here? So I will just tell you the formula because we're gonna use it later. So definition. So the surface area of X. So how do we compute it? Let's call it AX is, so AX equals to the double integral of D on this length of a normal vector cross together. So you need to cross two normal vector here over dA. So what's this D here? So I need to tell you what's D here. So where this D come from? So in that case, I need to tell you what is S then. So S is defined by this R UV, okay, such that UV is in D. Okay. For example, for our sphere just now, what's my D? For the sphere I have just now, where's my D? Where's my variable live in? So for phi is 0 to pi, and then for theta is 0 to 2 pi. Okay, so this is my D. Okay, so this is my D. And maybe you feel weird, why is the length there? 这么长度跑出来 The long, right? The length. Why is there the length there? Okay. So for these, there's some or the lying principle is lying 这样写忽然间忘记是这样写吗 Line principle. Okay. So the line principle is if you want to compute an area of a parallelogram, okay, it is just you take A cross B, so the area, so let's say A here, so A is equals to the length of A cross B. Okay, you should prove this. I'm not sure you did it in linear algebra, but apparently, if you have a parallelogram and then you take two sides, the cross product of two sides, you will get a what? What do you get? You should get a vector, right? And that's a normal vector. Apparently, the length of this normal vector is the area of this parallelogram. Okay, you should prove this. This is a linear algebra exercise. Okay. And so we do integration. Why we do integration? Because we need to consider every small parallelogram in the domain. Okay, so there's a picture. There's a picture in your notes here. Picture in your notes here. Okay, so there's a picture in your notes here. And not this one. This one. Okay. So this is related to the Jacobian also. This is related to the Jacobian. Okay, but we don't want to derive it. So let's test this formula here. Let's test it. So let's test it on our sphere. Okay, test it on our sphere. So let's test it on our sphere. So for example, so let's test it on find the surface area of a general sphere. Okay, let's don't fix the radius. Let's find it on the general sphere. Sphere of radius A. Okay, so have you memorized before? What's the surface area of a sphere? 有没有背起来过它的 formula? What's the surface area of a sphere? 4 pi r square. Good. 4 pi r square. So let's use this formula here. see whether we get 4 pi r squared. Okay, let's use this formula here. So how to parameterize this sphere here? So this is a surface, right? So two variable we need, phi and theta. Okay, and the x coordinate should be a sine phi cos theta, then a sine phi sine theta, and a cos phi. Okay, so what's my d here? So where should I take my phi and theta from? What phi I need to consider? What theta I need to consider here to get the whole sphere? Phi from 0 to pi, and then theta from 0 to 2 pi. Good. Okay, so what do we need? What's the ingredient we need for our formula AX here? So you need to remember our, what do you need to remember? Remember the area of a parallelogram, okay? So it's a length of R differentiate with respect to phi cross R differentiate with respect to theta here, okay? Yeah. So how many things you need to compute here? You compute this one, compute this one, compute this one, compute this one. Okay, go compute. Okay, I give you 2 minutes. 2 to 3 minutes. Try and compute it now. Okay, compute. Later we compare answer. Okay, I give you 3 minutes. Try and compute. Okay 啊，same 咯。What's your length 啊？What did you get for your length? I mean, yeah, length first. What's the length of the normal vector? What's your length? What's your length? 啊，平常算到了，你算到哪里了？哪一个？哦，哪这个算了？一样吗？不一样。里面放的东西一样吗？里面放的东西一样吗？看在里面放的东西，它就纯粹算很麻烦吧。里面放的东西一样吗？看在里面东西放一样吗？What's the length of your normal vector？自己算出来了。前面呢？两分呢？你什么不一样？你的 normal vector 不一样？normal vector 不一样？我有错没？我应该没有错吧？其他人的 normal vector 一样吗？不一样啊？我写错啊？一样不是？公平也是算到这个哦，还是我有东西写少？没有，还是我这个后面最后一个有写错吗？呃我后面这个写错吧？这个是滴答是不是？我看一下，滴答还是 five？啊 five 啊 five 啊不对，嗯，yeah five 对 five yeah five 对，因为是 cos square 滴答跟三的a square 嘛，少一个 a square 是吧？OK OK 对，少一个 a square 这个我全部都要是吧？OK thank you。A 还是 S square？S square，yeah，S square，OK，good。找一个 do 在哪里？第几个有 do？K 那个位置有 do？有 do 嘞？没有 do 吧？因为是 cos square theta 跟 sin square theta 切掉，呀，不是2倍，他们是加起来是1。OK 吗？OK 吗？这样子 OK 吗？看可以吗？那现在跟自己的答案对一下，OK 吗？算了，你要自己算了，不然等下考试不会算。OK，OK 啊。所以最后有没有算到这个长度是 x square sin Well, I mean, you answer 吗？这个两个可以 combine 吗？都是 do combine。If you combine, you get a square sin square 5。这个错没算错？下来，呀，我觉得没有算错。你可以 factorize 两个东西出来。First, you factorize a square sin square 5 and then you factorize a square sin a square in the right number after that. See. So first you factorize square theta. Yes. So you factorize a square sin square phi. This. Right. Okay. And then what else can you factorize here? 在哪里啊？哪一个？对啊。Okay. So can you factorize further? A4 sin square, right? So here got 4 sin phi, here got 2 sin phi. So you can put the 2 sin phi out. OK， OK 吗？全部 OK 吗？全部人一定要到这一步啊，我们才继续。Okay, until this stage here, so what happened if you put this length into it? Okay, 我怎么写 A 是 A 吗？哦 radius 是 A. Okay, good. So what's your D here? Still remember what's your D? D is going from where to where? So D is controlled by phi and theta, such that phi is going from 0 to pi, and then theta is going from 0 to 2 pi. Okay, so how to do double integral here? This D is what? What kind of rectangle is it? It is a polar rectangle, right? Okay, so this is a polar rectangle here. Is it a polar rectangle? Yeah. Okay, so how do you do integral here? But your function is already in theta and phi, right? Okay, so actually you treat it as a Cartesian coordinate now because your function already live in polar sense. Okay, so it is just a rectangle, so you should do what? You should differentiate. So by Fubini theorem, okay, how to differentiate? I mean, how to integrate the area? No matter how you pick the order, okay, you can either do d phi d theta or d theta d phi, up to you. Then if we do d theta d phi, then we'll integrate from 0 to pi for phi, and then 0 to pi for theta. Okay, so you do this integration here. Okay, I give you 1 minute. Try and do this. And compute this. Okay, I think one variable is constant, right? So which variable is constant? Respect to theta is a constant function, so we can straight away throw out the 2 pi, right? And then integrate respect to phi, you get negative cos phi from 0 to pi. So you should get 4 pi n square, okay, which is your usual formula for pi square. Okay, so that's why your high school asks you to memorize. If not, you need to go through all these. You need to learn linear algebra first. Okay. Before we can tell you the formula. Okay. All right. Okay. So there's a version for. So okay. Yeah. Oh yeah. Yeah, done. So there is a formula version for surface where you write it as z equals to fxy. Okay, we won't derive it for you. You can have a look, because even if you don't know or you forget this, you still can use this parameterized way to figure it out. Okay, yeah. So I just teach you one method. The other method is mentioned in the lecture note if you are interested. Okay. So before we break, let's introduce some more definition. So we will introduce surface integral. Okay. So let's do surface integral for scalar field first. Yeah, let's do it for scalar field. Okay, so meaning f x y z, okay, such that this number is in real. So let's define this first. So integrate over a surface of f x y z. Yes. Okay, so let's not go through all the definition. So let me give you the final answer first. So how do we do this? Let me tell you what's the final answer here. What should we do is we should integrate over d of f of your parameterized surface, okay, times the factor coming from the surface area. Okay, I want to ask you whether this formula looks familiar or not. Does it look familiar to you? Maybe. Does it look familiar or not? Okay, does it look familiar to you? So what's the relationship between this R here? Where I get this R from? What do you think? Where do I get this R from? I parameterize my X here, okay, such that I can parameterize my X using RUV. Okay, so this is a Riemannising. 哎呀，又写一个我不会的英文字哦。Riemannising 这样写，先忘记。Riemannising 会写吗？大家？知道什么是 Riemannising 吗？就是怀念，我有点怀念你。Reminiscing 怎么写啊？突然间忘记。Reminiscing。OK， 等一下 ，Reminiscing，太长了。OK， some reminiscing result we had last time. So what do we have last time? We do line integral on a scalar field. Yes. Okay. But what did we do? What did we do last time? We also parameterize our line. Okay, our curve. Okay. We parameterize it so that we are integrating f on this parameterized line here. But remember, what's the contribution here? Norm of r prime t. Good, very good. 对，没有错。Norm of r prime t. 看有没有很像？有没有很像？像吗？像吗？会不会像？哪里像？OK，I mean 这个是不像的地方，不对？不像不是，一个是 one variable， 一个是 two variable， 像的地方在哪里？像的地方在哪里？对 ，Yeah， right， derivative 对 把这边有两个，这边有一个嘛？为什么会有两个出现？因为你在 two variable 嘛。But still inside here is a vector 哦，两个 vector 怎么变成一个 vector？Cross product。cross product. And same thing, you evaluate your function on your parameterized curve or surface. And then there's an extra contribution from your derivative. There's an extra contribution from your derivative. Okay, man. So last time, how do we describe this? 还记得我们讲 describe 这个 integral 吗？还记得我们讲一个最重要的字 a magic word for this line integral？还记得吗 ？a magic word。关联 a curve. So you try to integrate along a curve with a height, right? Scalar function, scalar field. So 每一个点有一个号码，把它想成 height. So you integrate along that curve, 你就算有它的 area bounded before the scalar function. Then 你就可以想象这是一个串联。So how to 想象这个串联 ？So the curtain trace out a curve. Then the height is given by your function. Okay. Similarly here, 这边也是一样。You are no longer working on curve. You are working on D domain. Okay. 就是一个 一个 surface. Okay, 一个 surface. And then 这个 surface has height also. Right. I also attach height, a number to every point. Then what are you integrating then? Instead of area, you're integrating to get a volume. Okay, to get a volume here. So yeah, so where's the picture? Let me show you the picture. Okay. So this time your domain become surface like this, 2D shape. Okay, but in your double integral, multiple integral, you are working on R2, flat surface. Now we become curved surface. Okay, so this S is a curved surface. Okay, this S is a curved surface. It's like exactly the same story with line integral. In calculus 1, right? Your line is just S-axis, straight one. But now we do curve C. You can do integration. Similarly to surface, in multiple integral, you only do it on R2. Then now I upgrade to curved surface. So you can, like, for example, compute the volume over this chair, maybe. This one is curved already. And not flat. Maybe here still flat. Okay. Okay, so let's take a break until 10 o'clock. We'll continue.
没有6号的笔记，怎么了？没有6号的笔记，6号笔记是lecture 几啊？25，没有没？等一下啊，为什么没有呢？嗯，哪一个没有啊？你说 lecture 几没有？25啊？这个呢？这个不是25啊？25啊？没有，这个没有，这个没有呢？25不是在 week 是看一下，对啊，哎，这个就是啊，那我叫以前，上前几节，你要什么现在？这是我们当时的，就是我们那天的笔记嘛。应该啊，为什么不是？那这里为什么还有24？一个星期有2次啊？一样的。没有，一个是黑板，一个是我整理过的。啊，你平时是看黑板的没？你看黑板的，可是黑板的有时候不完整。这些功课我做出来看到，还真的不完整。或者你有那些那种放在桌面上面，小这些对我们是整个
Hello. Okay, let's do one example on this surface scalar field first. So if you look at this question here, we're doing a double integral, but this double integral is on a surface. Okay, so this surface is curved. Okay, so this is a sphere with radius 1 and center at the origin. Okay. What's this scalar field here? You see what's this scalar field here? X squared. Okay, so what does this scalar field tell you? The height only depend on the x coordinate. They only depend on the x coordinate. But x squared, what is x squared? X squared is like this one. So x squared is like this. Maybe let's draw it out first. So if you just look at y equals to 0 slice, where it's like this. Okay. But what are you looking at? What are you looking at? We are looking at on a sphere. We're looking at on a sphere. Okay, how should we imagine it? How should we imagine it? I think cannot imagine because it's an R4 thingy. Right, because you already need to draw your sphere in a 3D. Okay, so let's say, why my sphere disappear? So let's say x is in this direction. Why my sphere disappear? Then what do you see here? your number that you attach, maybe really cannot draw it because you need another axis. So let's say my x is here, okay, and then here is 0, right? So you can see that on the left-hand side, sorry, on the right-hand side of the origin, your height, I mean the scalar that you attach to this sphere is getting bigger and bigger, okay, until you reach the point where, what's this point? This point should be 100, right? 100 at this point. Okay. So 100 has the largest number. And on the other side, negative 00 has the number. And what else? Yeah, that's all. Then you have this decreasing and then increasing when you pass by the origin. Okay, so how to integrate this? Well, the first thing you do is what? You need to transform your curved surface to a flat surface first. Okay, you need to transform it to a flat surface first. So you need to transform it to a D first. So how to transform it to a D? Yeah? So you need to parameterize your surface. So how to parameterize your surface here? Just now we do it already, right? So it is r phi theta. Okay, r phi theta, and then such that what's the x coordinate, y coordinate, z coordinate, sine phi cos theta, sine phi sine theta, and cos phi. Okay. But remember, what happened here? Actually, there's an extra factor here, right? So the extra factor is what? You need to compute what is the area, okay, of the parallelogram. So in this case, is the norm of your normal vector to your tangent plane. Okay, and you parameterize your surface already. What's your s coordinate here? Your s coordinate here will become sine phi cos theta. Okay, so you need to compute this. Okay, but just now we compute the formula for this normal vector already, right? We compute it for a more general case, which is a squared sine phi. So a in this case is 1. Okay, so we should get this integral to be sine phi cos theta squared times sine phi dA. Okay, but this is over the whole sphere, right? So your d phi and your d theta should be taken from 0 to pi and 0 to 2 pi. So you integrate this whole thing of sine cube phi times cos squared theta. So you integrate this. Okay, maybe we don't do it now. So if you do this, you will get 4 over 3 pi. Okay, does it make sense? Okay, so there are a few things to do here. First thing is you need to know how to parameterize the surface. After you parameterize the surface, you need to find the 2 tangent vector. Okay, what's the 2 tangent vector? This is what you learn in partial derivative. You differentiate with respect to the 2 directions. And then what do you do next? You take the cross product, because you need to figure out the normal vector of your tangent plane. And then you compute the length. Okay, it's like what you did for your arc length. You compute the length contribution from the when you do this transformation. And then for the rest is just multiple integral. For the rest is okay now. Okay, so the idea here is I don't know how to integrate over sphere, but I can make this sphere into a flat surface. Okay, so this is the idea. So this is coming from the chapter of multiple integral. Okay, so I turn an integral on a surface integral to a multiple integral question. Okay, so this is the key point of this chapter. Okay or not? Okay, So this example we won't go through, but if you look at here, how should you do it? Let's briefly discuss how we do this. So we have surface integral again. Okay, so this is just a z scalar function z, meaning what? This scalar function depends on z. How high is your z? Then it's what the number I attach. And S is a surface. What surface is this? So this surface built out by three things. So the side is given by a cylinder, and then bottom is given by this, and top is a special one. Top is a plane, length of plane. Okay, so you can see that the let's say the intersection. Three formula that govern this three part here. X1, S2, S3. One thing you need to know is there's also a linearity for surface integral. Okay. So you can see that our surface is built up by three surfaces, S1, S2, union, S3. And their intersection is what? It's just curve. Right, their intersection is just a curve. Okay, for example, X3 intersect X1 is what? Is a circle. Okay, S1 intersect S2 is just a point. Okay, and then S2 intersect X1 another curve. Okay, so these are finite number of curves, so it is linear, so you can use linear. X, Y, Z. Yes, you can split it into three parts here. Over X1, over X2, and over X3. Okay. Then for these three parts, you need to do what do you need to do? Do parameterization. Okay, you need to do so there's a technique involved here. Well, I mean, in the exam, if you write like this, you will get some mark. Okay, the next mark is to parameterize your surface. Then also compute the normal vector, length of normal vector, and then compute the integral. Okay, so this question is kind of long, actually, quite long, because it involves a lot of computation. Okay. OK， 看一下我们有没有时间做这题，我想一下，你们要做吗？我想见我有没有时间？我们怕有没有时间？我们还有2个 Theorem 啊，可以哦，你们回去做先，然后 revision week 我们可以再讨论题目。呀，可以的，呀，我们可以再回来讨论这些题目。I think today focus is I need to teach you the method first, and then you go back try, and then 不能，我们 revision week 再讨论题目。我们就 go technical 一点。现在我先告诉你重点在哪里，然后你记住这重点去 try 题目，然后我们再会来讨论 technical 的部分，算错还是犯错东西。OK。Next thing is about giving an orientation to surface. Like last time, right? We also give orientation to our line or our curve. Okay. So two orientation we can give to our curve, positive or negative. So similarly here. So let's orient surface here. So before we define surface integral for vector field, okay, we have line integral for vector field, which is the word done. Okay, we also can do it for surface integral. Later I'll tell you what's the physical meaning for surface integral of vector field. So where's the orientation? 没有 define 真是的，没有 define. Okay, never mind. 我用举办的。Okay, so what's the orientation of surface? So on the surface, right? You can imagine a plane.先 start from plane. Okay, so start from a plane. What arrow you can give to this plane? Actually, there's a natural arrow you can give to this plane, which is the normal vector. Okay, if I give you a plane, there's a well-defined normal vector here. 而且每一个点的 normal vector 的方向都是一样，虽然只是位置不一样，对吧？Okay, one normal vector can define the plane. So on that vector, I can choose whether you go up or you go down. And so this is the two orientation I can give on plane. Maybe 我画出来。Okay, given you a plane, you could have a normal vector. So there are two directions you can give, either going up or either going down. 两个方向。Okay, to this vector. So this is what we mean by giving orientation to a plane. After we can give it to a plane, we can give it to surface. So why? How to figure out a plane from the surface? On surface, you're not on plane. Tangent plane. Okay, if you have a differentiable surface, right? If you work on the surface, you can find tangent plane to that surface. Then, over each tangent plane, you can choose your orientation. You can either 往上或往下. Okay, and then there's one example here. Okay, there's one very good reason why they put this example here. We have a Mobius strip. Anyone know what a Mobius strip is? Obviously, I don't know translation, but we don't really know. Okay, 如果谢谢可以写在题。什么是 Mobius strip 呢？ So you start with a strip. Okay, you start with a strip, and then on two sides you glue it together. Obviously, if you are glue is a cylinder. Okay, but instead, what do? You flip the side, and then you glue it together. Side. Like this. What's this? What's special about this Mobius strip is there's only one side. Every cylinder there's two sides, 对吗？你的 sprinkle 是不是放在 cylinder 里？ But 这边只有 one side 吧，没有里面和外面。Why? If you try and walk around this strip here, okay, you will return to the same point you started with. Okay, why I say this is not orientable? Orientable meaning I need to give a direction, right, on your, let's say there's a tangent plane at every point. If I say my orientation is give every point going outside, 往外的，然后就往外走。Okay, so let's start from here. 看啊，全部人看这个啊，往外哦，我往外啊，这个点往外啊，看一下，等下我回来这个点发生什么事情。If I walk around this Mobius strip, right? Walk around. 走错了。回来时候 if we come back to this point, right? Actually, it is contradicting what we gave, the orientation we gave at that point. You give up, but you walk around continuously coming back to this point. Actually, it points down. And so there's no consistent way to give orientation to this surface. Okay. So maybe 你可以问我，怎么我要走呢？这个就是一个this orientation, right, should be preserved by these continuity. Now I can pass around. You can play around. You can pass. I can try and work on this Mobius strip. 我要钉在比较好，我钉在里面。OK， 我回答。Yeah, I will pass around the Mobius strip. You can walk around along the Mobius strip. Okay. So what's important here? What's the important thing here? So the important thing here is about closed surface actually. Okay, actually about closed surface here. So there are two orientation we have to define on the closed surface. One is positive, one is negative. So for the positive one is the one that having the normal vector pointing outward everywhere. Okay? And the negative one is pointing inward. Okay, so this is like the line zone. We also have positive, negative. What is the positive orientation for a line? Clockwise or counterclockwise? Positive orientation for closed curve. Counterclockwise. Okay, so counterclockwise. So for surface, it's going upward. No? It's like a durian. Okay, durian going upward. Okay, durian. Okay, so now we'll define surface integral of vector field here. Okay, vector field here. So how do we define it? So this is how we define it. So we define a surface integral of a vector field, okay, as the surface integral of f dot n. Okay, f dot n here. So what's this n here? So this n is kind of important. So this n is the unique normal vector. So meaning what? This is the normal vector to your tangent plane. Okay, here. Normal normal vector to your tangent plane, but dividing by the length. Okay, 被 length 除。所以刚才你算的那个 length 还是很有用的，现在继续还会用到，所以你一定要会算这个 length of vector 的 normal vector. Okay, you must know how to compute the length because we are continuing to use it. Yeah. Okay, so 你可以看到here 这边是什么 ？Okay, so let me point out to you. So on one side, this is a surface integral of vector field. Okay, so what you put inside your integral is a vector field. But here, this will become what? Surface integral of a scalar field. After you take in product, what do you get? You get numbers. But these numbers depend on point, it becomes a function, so scalar field. So we define surface integral of vector field using surface integral of scalar field. But how do you make this vector field or the vector become a scalar field? You need to dot product with something. Right. Just now we cross product to get a vector, right? Now if you want to get number, you use dot product. But what are you dotting with here? What are you dotting with? This is the unique normal vector. So unique normal vector means what? Where the normal vector comes from? The normal vector comes from the tangent plane. Okay, so you should take RU cross RV. But unique means what? The length of the vector is 1. So you need to divide by the length of that vector. Okay. Okay, maybe we try one question. Let's see. Let's see. So again, 同样的，我们用圆圈先。哎，怎么这个没有呢？有后，不在这边。Let me see. Well, I mean, 我们用一个比较熟的 example. Let's use this one. Okay, use this example. Complete. Okay, let's use this example here. Let's erase everything. So let's do this example here. So let's find the flux. Okay, I haven't teach you the flux. So another name for a surface integral is what we call a flux. Okay, flux. So do you know what's a flux? You think of flux. For example, magnetic flux. 你的磁场有多强？磁场。你的磁场 ，OK， 磁场 flux。 Okay, magnetic flux. So let's try compute this. Well, let's integrate this function vector field with respect to Ex over this sphere X. So how do we do this? So by that formula, right, you should do it on S, but F have to dot with a normal vector here, and then ds. So here S is a bar. Okay, so there's something to note here on the right hand side, left hand side. Right hand side here, what do you have? So let me point out the object first. Here is vector field. Okay, here is vector. But here, after you dotting, it becomes a scalar field. Okay. Okay. So this is how we make the D of a vector field disappear. How do we make it disappear? We just look at the normal vector. We won't derive, but you can check the notes if you like. Okay. So technically, what's the difference that we did just now? What's the difference? Technically, 刚才做的 multiple integral 跟现在做的 multiple integral 有什么差别？多一个 normal vector 不止哦，你要动那个 normal vector， 什么东西要动那个 normal vector？vector field， 刚才我们玩的是 scalar field， 现在我们玩的是 vector field。OK，so meaning what？ 来，我们再写清楚一点。So this F is a vector now, Z, Y, and X. Okay, you are dotting with a normal vector here. So what's this normal vector here? It's not just a normal vector, it's a unique normal vector. So meaning what? You need to divide by your length. Yes. Okay, ma. Okay. Okay. Hey, 这个不是after you dotting this, go back to the previous question, right? But 很神奇的是很神奇的是 but still remember just now when we do this scalar field, what do we need to do? This is equal to what? Integrate over the domain. Domain of what? Domain of this scalar field times what? Times the norm of normal vector. 所以你看到什么？其实它是会 cancel 掉的。当你最后再算的时候。So this norm, right, of this normal vector will cancel. Okay, when you try to do the surface integral for your scalar field. How you cancel? So 你真的就是算这一个 dot。OK 了，要不要算算看 ？Do we try？ 要不要算这个 example 算算看？看现在会不会算 ？So how to parameterize this 我们一整天都在 parameterize 这个 sphere。OK， 来算一下这个 sphere。Is sin phi cos. It's a very good running example here. Sin phi. 90 theta and okay, good. 其实很多号码你都算过了，对不对？他们已经算过了。with respect to U 是怎么 respect to B 的？我们其实算过了。那虽然我们也算过了。Okay. What we haven't computed is to substitute this into your vector field. And if you substitute this into your vector field, what do you get? So here is cos phi, sin phi, sin theta, and then sin phi cos theta. You dot with your cross product here. What's this dot? What's this dot? So you have computed it. So sin square phi cos theta, sin square phi sin theta, and then sin phi cos phi. Okay, 很多东西。Yeah. Okay, so a bunch of trigo. Bunch of trigo. If you computed it, should be 4/3. 来得及算吗？来不及。OK， 不要紧啊，可以回家算。I think我想actually I will give about 4/3 marks are given to this. Okay, even if you cannot complete. What's the end? 4/3 marks and give to this step. Okay. 如果你后面呢搞砸了啊，就1/4的分不见了，大概。哎，讲错了 3/4。讲到华语版跟英文版混在一起。华语版跟英文版混在一起。Okay. Yeah. Okay. So let's continue. There are a few examples in your notes. You should try it out. 你们 assignment 我出什么题目啊 ？Stoke 还是 Divergence？ Stoke 还是 Divergence？ 感觉是的。其他人用什么解 ？assignment 最后一题 ，Stoke 还是 Divergence？Stoke 啊 ，Stoke。OK Stoke， 全部人做得出吗 ？Stoke 有自己 try 吗？还没有 try 啊？我交先 ，OK， 好，我交先。OK good， 来我们交先。So let's talk about Stoke's theorem. So what's this Stoke's theorem about? It's like Green's theorem. What do you need for Green's theorem? You need a closed loop first. Okay, so here is the same. So let's say you have a oriented surface, okay, and then you have a unique normal, and then this surface here has a boundary. Okay, has a boundary. So there's a person here walking on this boundary. 有个小人。So what? So like last time, what did we say? What's Green's theorem about? The closed loop is in a positive orientation. Then when the closed loop is in a positive orientation, it bounds a surface. Then the surface is on your left if you are working on that. Okay, so this is the same. Yeah. So what's the Stoke's theorem here? So instead of starting with curve, we start with an oriented piecewise smooth surface, and then this piecewise smooth surface is bounded by a single closed curve. It's the exact same condition you have with your Green's theorem there. But now we have a clean way to talk about Green's theorem. No? If you want to do a work done around this curve, okay, f dot dr, it is just what? Computing the curl of this f. Last time I'll show you. But this is a more general one. For Green's theorem, it only works for 2D. But here is a 2D in 3D. What does it mean? It means that you can look at any parameterized surface. Okay, this surface can live in 3D. Okay, maybe it's worth to do some exercise. So how about do this? Let's do this. Verify the Stoke's theorem. Okay, using this vector field y minus x and yz. Let's say your surface is a paraboloid. Z equals to x squared plus y squared. With the surface x squared plus y squared equals to 1.
and z equals to 1 as the boundary. Right, so what's this? What does this mean? Let's see what it means here. So where's the surface you need to consider? What's the surface you need to consider here? How many surface you need to consider for this case? How many surface you need to consider here? Huh? 2. Okay, good. 2. So where's the 2 surface here? Where's the 2 surface here? Z equals to y. Z equals to 1. Okay, so this is this thing here. So x1. And also the paraboloid here. Okay. So do you know where's the boundary? Where's the boundary of this curve? Where's the boundary? Huh? You think that this is the boundary? This is the boundary. Okay. So I mean, if you treat x1 and x2 as both of your, both of your surface, actually there's no boundary. Like a sphere. Is there a boundary to a sphere? So meaning, can you find an open neighborhood such that the point is the neighborhood contain point outside, inside the sphere? No boundary. This is exactly the problem of our Earth. 就问过一个问题：怎么你走到海的尽头，你不会掉下去 ？No boundary, there's no boundary. 你海的尽头还是海，哦，你走到陆地。如果你是 ，OK， 你不会掉下去的。There's no boundary for sphere. There's no boundary. Okay, so if you want to include that green line as your sphere, meaning you are not considering S1 and S2 actually, you are just considering S2. Okay, you just consider S2 actually. So in this question, I think they only consider S2. Okay, just the paraboloid. Okay, so they just consider this paraboloid with the circle S. So you see, so this is the point here. Okay, so we need to read it properly. So where's the boundary here? Already this question tells you already. S squared plus y squared equals to 1, comma z equals to 1. So you should read it like this. This is the circle. Because if I tell you s squared plus y squared is to 1, in 3D, this is a cylinder. This is a cylinder. So I need to tell you which circle. The z equals to 1 circle. So this is the. So to describe this boundary, right, you really need 2 equations. Okay? Does it make sense? Okay. All right. So let's do it one by one. Okay, let's do it one by one. I'll guide you how to do, and then I will let you compute. So let's say we want to integrate over this curve here. Okay, this curve should be oriented positively. So positively means what? You need to orient in the counterclockwise direction. Okay, so this is a curve. This is a circle. So circle, how to parameterize? Huiqi, I think you are professional in this already. So how to parameterize a circle? What's the x coordinate? What's the y coordinate? What's the z coordinate here? R cos. So what's the radius here? A 是什么 ？E okay E. So what's your x coordinate? Okay, in this case 我们用 t. Okay, and then y coordinate. Okay, height 呢？有高度吗？这个 circle 啊 ？E y z equals to 1. Okay, good.
So this t going from where to where? 0 to pi. So if you do this loops integral, what do you do here? 啊，刚才一翔跟我们讲什么 ？You need to parameterize your vector space. Sorry, vector field. And then what do you do? You take your f dot with your r prime, not r prime. Okay. Here. Dt. Yeah. Okay. So what do you get here? Well, what's r prime t in this case? You get negative, not negative, negative, yeah, negative sine t, cos t, and then 0. Okay, so you dot these two together. Yeah. Try and compute, see what you get. So you really see similarity in the surface integral for vector field. You also take dot product with your derivative. So you can write your f with RT. Okay. So let's see if you get the same dot product or not. You get minus sine square t minus cos square t. Get this? You get this? Minus sine square t minus cos square t. It is? Okay. So, well, you integrate this, you should get minus 2. 有吗？有拿到吗？没有拿到，看一下哪个地方不一样。Yeah. 其实在学数学不是很简单吧？数学复杂也简单。为什么简单呢？其实数学在做的事情就是分辨一样跟不一样，一直分辨的东西就是一样，什么东西和什么东西一样，什么和什么东西不一样，对不对？就说很简单的检查答案，你看到你的答案跟别人答案不一样，是不是有错？然后就去研究，如果一样的话，看一下步骤一不一样，可能可以不一样。然后这个一样和不一样哦，当你学深一点数学哦，它概念会变。可能两个完全看起来表面上看起来不一样的东西，但是呢，它们的 structure 是一样的。你升学过后，你到 second year， you will learn something called group rings 啊，这些东西就 capture 不同的 number system 一些结构或者架构，或者叫 structure。OK。OK 吗？全部人算到吗？有问题吗 ？OK。If no question, let's compute the surface integral of curve f now. Okay, let's compute curve f. So to compute curve f, what do you need to do? Few things you need to do, right? Obviously, first thing first, you need to compute what is curve f. So let's compute curve f first. So still remember what is curve f? You are taking the normal, the gradient function, gradient vector, cross with your vector field. Okay, take your gradient vector, cross with your vector field. So in the end, what do you get here? So you have del over del x, del over del y, del over del z on one row. The other row you get y equal y minus x and yz. Okay. So altogether here, what should you get? 你会算到什么东西 What do you get here? 能够直接看出来吗 You should get z 0 and minus 2. OK 吗？可以吗？算这个 cross product。有问题吗？全部人 about this cross product， 你一定要学哦，因为我们会用到这个计算。眼睛 check 得到吗 ？By inspection， 眼睛 check 得到吗？这样子。And then 这边跟这边，可以吗？眼睛 check 得到吗 ？By inspection。Okay. Right. So this is your curve phi. So meaning what? This is the vector field. You need to integrate over. 对吗？是 vector field 吗？是哦。Because even x, y, z, you also have 3 the vector field. And then now we need to do the surface integral. So how to do surface integral here? So meaning what? You need to parameterize your S now. So your S is this truncated paraboloid. So it's a truncated paraboloid here. So how to describe this X? How should we describe this X here? So let's write down this X first. So this is a paraboloid, but you truncate it. So how do you truncate it? Well, you only take xy such that x squared plus y squared is less than equals to 1. Okay. Is this how you truncate it? You take all the z that is less than or equals to 1. Okay, meaning you take all the xy that satisfy this condition here. Okay. So maybe put different z. So here z2, here z1. But what is this? This is what? This is a disk with radius 1. Okay, so this is a disk with radius 1 actually. Okay. So meaning what? Meaning where you get this paraboloid from, where you get this point from. Actually, you are getting from a disk with radius 1 point here. So 你可以想象你是一个 disk of radius 1 and 它包上去，对吧？包上去。Okay, using this z. 可以想象吗 Okay. So you use this disk of radius z to get this surface. Okay, make sense? 懂我在讲吗？Okay. So well, I mean, so you can see that this is a disk, right? So a better way to integrate is what? A better way to integrate is what? Maybe you can also consider the what? Instead of integrate over xy, you can make it over polar. Then you can make it over polar. So you can write it in a polar form where your radius is going from 0 to 1, and then your theta is going from 0 to 2 pi. Yeah. Instead of doing it in xy, you can do it in theta form. So how all these work together? So how all these work together here? So we haven't yet parameterized these surface. So how should we parameterize these surface? What do you think? What do you think? How to parameterize this surface here?
Actually, right, this z equals to x squared plus y squared give you a hint how to parameterize this surface here. Okay, what does this equation tells you? It already tells you the third coordinate. Okay, it already tells you what happens to the third coordinate here, which is x squared plus y squared. Okay, how about the first two coordinates? What do you think? Do I do anything or not to x and y? No need. I just use x and y. Okay, and then this also align to how we understand this curve, right? This surface. This surface is given by this here. So you just attach the proper height to this, then you can get your surface using this this. Does it make sense? If I gave a proper height to this here, I can build up the surface. 对啊，就像一块布哦，一块布本来是布这样，然后有包起来的时候有 give height to this point of the cloth, and then you can make out the surface. Okay, so I mean, in the surface, right, you always have two linearly independent. Okay. All right. So what else we need in our computation here? So let's write down the formula first, and then we'll figure out what we need. Okay. So how to compute this surface integral for vector field? We need to make it a surface integral for a scalar field first. So how to make it into a scalar field? We need to take this curl f dot with the unit what? Unit what? Unit tangent. Okay. Unit normal vector. Okay, unit normal vector. Okay, unit normal vector. But like what I showed you just now, right? If we go through the process, we will see that the length of this unit vector will cancel with the factor of another length of unit vector coming from the surface, from the surface integral of a scalar field. So what you really need to do here is you take your curve f dot with your rx cross ry. Okay. So in the end, what do you need? What else you need to compute here? You need to compute what is rx, what is r1, then cross them. Okay. So let's quickly compute it. So what is rx? What is ry? And then what's the cross product here? So Rx is simply 1, 0, 2x. And then Ry is 0, 1, and 2y. So if you cross them together, what do you get? So quite the cross is here. So what do you get if you cross them together? Do you see minus 2x, minus 2y, 1 here? So well, I think 1 比较容易看的，就是一乘一点零点。About the others, maybe check one of it. The x position. So x position is about making a cross conjugation here. So one side is 0, the other side is 2x, but there's a minus 2x there. Okay. One thing you need to check here. Is whether this normal vector is in a positive direction or not. Is it in a positive direction? So let's look at our surface here, and then try and put this vector back to our surface. So for example, where? Let's see. Example where? Well, I mean, let's see. Let's check. Is it in the positive oriented version? Okay, so what do we mean by positive orientation? Last time we said that it must look like a durian like this. Okay, so the vector, if you evaluate this normal vector on the point in your surface, it should be pointing upward. It should be pointing upward. Is it true? Negative. Negative means what? This is a negative orientation. Why? Have you drawn it up? Have you tried and draw it? Have you tried and draw it? So is it positive or negative here? Have you tried and draw it? So let's try and draw it. Okay. So should we draw it? If it is on the, okay, so let's draw it up. X, Y, and then Z. Okay, so if this is the origin, then what happened at the origin? What's the normal vector we attach? It is 0, 0, 0, 0, 1. So 0, 0, 1 should be going upward. So the origin, it should be going 0, 0. How about different x, y? How about different x, y? Maybe you can check on some important point first. So what are the important point here? Let's see what are the important point. Well, I mean, let's check on this point. How about this point here? If we check on this point, what's this point? So this point should be 1, 0, 1. Okay, let's check what happened on 1, 0, 1 here. So in 1, 0, 1, you should get, okay, so let me, 0, 0, 1. This, so let's plot this point here. This is a 1, 0 point. Well, I mean, yeah, so this point is 1, 0, 1. And then what's the tangent, what's the normal vector we attach here? Is negative 2, 0, and 1. So negative 2, 0, and 1 facing where? So facing negative 2, 0, and 1. Facing inward and then a bit upward. This is the vector we attach. Okay, and maybe we test one more. So how about this one, opposite point here? Negative 1, 0, 1. So what's the normal vector we attach here? Should be 2, 0, and 1. Okay, so if you try and plot out all these vector, right, you should see that the normal tangent vector is like pointing inward. Okay, so this is a negative orientation. This is a negative orientation, is it? Yeah. So should we put a positive orientation on it? So meaning we need to consider the negative of it. Is that right? Seems like it. But why the answer here will match up if we use the... Okay, so let's continue first. I think something wrong in my calculation, but let's do it here. So
if we continue, what should we do here? So what's curl F? Curl F is computer curl F, right? So Z 0 and -2. And then Rx cross Ry should be negative of -2x, -2y, and 1 here. Over dA. Okay, over dA. Okay, so what do you compute here? How do you compute here? So how to compute here? What to do here? So this is integral over xy coordinate, right? So you can do it on polar coordinate. Okay, so you can turn it into polar coordinate. So before you turn it into polar coordinate, right, can we expand it first? So let's expand it. What do we get here? So over this Z, so Z is on the surface, so we should substitute to x squared plus y squared. Okay, so if I expand it up, what do I get here? I should get 2x times x squared plus y squared plus 2 d dA. Okay. Well, so we have turned it into a polar coordinate. So let's use polar now. Let's do it on polar. So dr d theta. So remember that when we turn it to polar, there's an extra factor r, right? Okay. And what? So what happened to this change of variable here? So we make it into -2, so 2 times r cos theta r squared r squared r. Okay, this part is correct. How about the other part? Plus 2r. Okay. Okay. So what's our radius and theta? Just now we fixed already, right? So our r is going from 0 to 1, and then theta is from 0 to 2. So what are you getting here? Seems like you get 2 pi. Correct? You get 2 pi. First part here, I think this first part has integral 0. I think the contribution comes from the second part. Why? Direction is different. How come? Why the direction is different? Do you get 2 pi or minus 2 pi? Do you get 2 pi or minus 2 pi here? Weird, direction different. Huh? You get 2 pi, right? But previously, why is it minus 2 pi? Why there's a direction different here? Can we fix this before we take a break? Let's fix this. What's wrong with it? Positive orientation, pointing outward. Correct? Pointing outward. Oriented, positive. Oh, wait, I think I'm a bit stupid here. Am I stupid? Oh, okay. I think I'm a bit stupid. Okay, so there's nothing to change here, actually. There's nothing to change here. I confused with divergence. Later, I'll tell you, I will introduce divergence. Where divergence, we really need a positive orientation on something. But now, no need. Now, no need. Now, it's just depending on the orientation on your curve. That's all. Okay, yeah. So, no need. So, no need to make this positive, actually. So, no need to make this positive. Okay, no need to make positive. Later in the divergence theorem, we need positive
orientation for closed surface. Okay, no need to make positive orientation on surface. Okay, so the takeaway here is we only need positive orientation on curve or the closed curve or Stoke's theorem. Okay, so we put back the negative. Let's put back the negative. Okay, yeah. Otherwise, we orient too many things. So we should orient the boundary, and then we just call whatever that surface gives us. So don't confuse, there's some that really unique. So you need to see what's your orientation of your line. I mean, of your curve orientation also. Later we will use it in Divergence. Okay, so we will say that so there's an upshot here. Stoke's theorem is a generalization of Green's theorem. Okay. So why is it generalization? Because we apply Stoke's theorem on surface, and not just the surface on R2, but general surface. Okay. Yeah. Any questions so far? Question? What's your assignment question about? I see. What's your assignment question about? Let me see. Assignment 5. Okay, so this is your assignment question 5. So you try to evaluate a line integral here. So this line integral here, L is f dot dr, right? So it's over a vector field, okay, dot dr. So meaning what? You are computing the work done. Okay, but this work done here, what's this curve here? Where you get this curve from? This curve is a triangle. Okay, triangle with 3 vertices. Meaning what? This triangle is a closed loop. Okay, so there are a few ways to do this. Either you go and parameterize these 3 sides. Go and parameterize. Okay, you can parameterize these 3 sides. And then you directly compute the line integral. Or you make a loop, okay, positive oriented loop, such that this line integral will be equal to the surface integral that bound by this loop, where you use what? You use the Stoke's theorem. You cannot use Green's theorem because Green's theorem live on R2. So because the surface you bounded by this triangle live in R3. Okay, so you need to use Stoke's theorem if you want to use Stoke's theorem.这什么叫都可以？不限制，没有肯定不限制。但是方法是在这个课里面，不是完全都可以，都可以。我没有讲 must use Stoke's theorem， 可以直接算的。什么？如果你能够 parameterize 那3条线，直接算咯。如果你想要做 curve 的，还是做 surface 的 ，then you need to figure out the plane that have this triangle. After you figure out the plane, then 就是一个 multiple integral 的问题啊。then 你要从 x 的 direction 要怎样 ，y 的 direction 要怎样 ，z 的 direction 要怎样。也没有 z direction，就 x 和 y 吧，对不对？
Okay, so if you solve this using surface integral, this will turn into a multiple integral problem. No? If you solve it directly using a line integral, then this is just about parameterizing the line. 有一条线是最简单 parameterize 的嘛，对不对 ？Because it's living on xy plane。还有两条线是有 involved z direction， 所以它的难度在哪里？ Okay. Either way, you can do it. You have to do both ways also can. It's good if you do both ways. Then this will make sure you know all the concepts. You know how to parameterize line. You know how to use Stoke theorem. To use Stoke theorem, you also know how to parameterize surface. If you can do both ways here, is good. Meaning you know all the concept already. Okay. 今天能教吗？还是你们要 extend？ 要 extend。可以啊，我们可以 extend。拜一 Monday midnight。Okay. 如果 if we extend assignment 5, right? How about project? Wednesday? 还是你们要同一天？你们整个 weekend 做得完这些全部东西吗 ？Project 加这个 assignment， 交得完吗？看一下，我看一下 majority 在哪里。assignment 跟 project 能不能够下个拜一起交？包含 correction 和 project。你不能，你不能。还有吗？其他人呢？能还是不能？能，不能。OK， 还有吗？还有谁不能？3个不能。OK， 还有不能吗？还有不能吗 ？OK， 如果这3个不能，我们就 grant extension to 这3个吧。你们要拜几家？拜3。啊？什么？什么东西？你讲吗？你要刚没几家？属于要刚没几家？现在先看一下有几个人先。如果是少数，我们就 grant extension 吧。那你看其他人呀？会扣分吗？如果是 grant 的，当然是不会扣分哦。呀，你们觉得怎样？还是全部人要慢？全部人要慢 ？OK， 可以。So assignment on Monday， project on Wednesday。OK， 我再慢下去改就很慢了。Yeah，OK。So assignment on Monday， 所有的 project on Wednesday，and then 我会给你们那个instruction 呢 ，about compiling 你的 project 跟你的 Turnitin。但是箭头你 compile 错哦，你没有拿你的原本的那个 report send 给我，你就发我那个 Turnitin 吧。然后还有一个人是没有给我那个 Turnitin report， 他只给我一个 Turnitin receipt。因为买菜有 receipt 吗？有 receipt 吗？没有那个 highlight 的东西啊，我切不到啊。OK，please please do it properly 啊。I'll give you a instruction, similar instruction 啊，其实就是 cover page， report，and then 你的 beamer，OK，turning in report。beamer 不用放进 turning in 啊 ，beamer 不用啊，就你的 report 放进 turning in 吧。因为你的 beamer 也是 mostly come from your report, right? So you just check your report 也是。有问题吗？信号就会被关。有 maintenance 咩？
管是管你的 project one project， 管是管你的。
是他关的，母的应该不会关。
我只是管就是。
除非有 maintenance 他才会关吧。Okay. Okay, let's take a break. We'll continue with divergence theorem. Wait until 1123.
哎，
你这个会觉得
对，
放在这个 first pass 里面才
什么意思啊？
是才是
就是看你拿几分，然后如果我有建议你要改一些小东西，还是有改的东西，你就会改哦，发给我，然后我会给 extra 2分哦，最高。嗯，你满分就不用改了咯，因为有些人还没有满分，有些就是
我以为不可以，
什么意思？
他没有放在这个这个
对，然后怎么？
我以为不可以，他是
没有，不是，我上面一个就是说可以给人家读了，已经完整了，没有大问题，没有逻辑问题。OK，等一下我解释一下，等一下我解释。
我去年的时候让我解释一下那个什么，就是那个审查。
对，
我查资料查的特别多。
对的没错，不能来简短说进去。
简短的话，那个不是只能写2页吗？其实已经有2页了，反正看了一下。
OK，
但是这个地方要加进去的话，就是
写了重点。
写它的重点嘛。但其实我没太看懂它这个是什么。
对，可能你要找一下它重点的，可能你需要消化一下再讲。
就
可能不用它太仔细的东西啊，但是就是消化一下它的。
就简短的说一下它是什么。好，行。老师那些 project 的万次改了之后，交到 Moodle 上就直接。
对，等下我会开一个 link，然后也是交到 Moodle 上。对，我开。
非常是。
对啊，这些选什么？你讲吗？
这些东西我应该分开教还是？
就是你有看到我 Moodle 的那个 instruction 吗？看一下我 Moodle instruction。
现在教的东西还差一点。
你没有给那个 original 的，就是原版的。你原版的 PDF。
原版的我不认。
你没有放你的原版进来，你只放那个你的那个被highlight 啊，你没有放原版。这个，对，其实这一个就是要用到uniform conversion，这个就是要用到uniform conversion。
哦，这个我是 proof 像 induction 类似 induction 的 idea，就是你先 proof 它，就是 proof 上面这一个先，你 proof 因为这个已经 shown 了它是 differential 了嘛，然后拿 integrate 回去，然后你就拿回这个 function，就是 fx
对，你要 prove 什么？
这个我 proof 的是这个 n 加1，因为我现在是 n 点1嘛，然后 proof 回去变成它的 original fx。
我想一下，不应该啊，不应该这样 proof 啊，你就是 proof for infinity 啊，你不是 proof for 有2个差别，你知道吗？就是 like 你要 proof 的东西是 OK， 一个是 pn， 不是 for on， 就是一个情况，你这个情况是 p infinity， 这2个情况不一样，所以这边没有什么 induction 用 ，induction 是这个，这个是说每一层都要对，你这个是就一层吧，你就到 infinity 都要对，它不一样这个东西，因为呀，这个是每一个 finite 对，这个不是每一个 finite 对，这个是但是这个 infinity 跟 finite 有关系，像你 introduce， 你有 introduce 吗？就是那个 Taylor remainder， 帮你 introduce， 就是如果你 truncate 它的话，它是一个，它会剩东西在后面。啊，这个 XM， 这 XM 呀，这个 partial sum 哦，这个是 finite 的。这个你知道什么意思吗？就是说它把前 n 个减掉过后，后面剩下那些东西是小于这边。对，你somehow要用到这个东西了。你需要这个 uniform conversion， 你才可以 swap 那两个。哎，你要比吗？要大改是吗？我觉得就不用改，不用改。不会了，不会了，I mean 不会了，不会，因为如果你是在 report 里面改了的话，就知道你有那个有变化。I mean 讲改呢，我觉得没有好改的，因为大改是吗？要大改嘛，可是要写很多东西，加很多东西啊。
还好，
如果你可以加，你就加哦。
加在笔吗？
呀，一起加，是不是反正一样的东西是吗？对吧？呀，你就，I mean 你最主要是把你的 report 写好，其实
下面的 OK。
下面什么？那些应该讲一下，我觉得应该没有什么问题吧。
它需要的一些处也不是处理，这个环境的那种介入，要不要写在前面的上述这个？
没事嘞，
有一个 environment，就是
我知道你 environment 给谁？
就是给这种
你要 prove 吧？
就是需不需要前面那个 environment 列出？
就你在说什么 theorem 嘛？
哈哈，
对，哪一个是 theorem？我现在问你，
就是
这是 theorem
对
law 啊？你是说那个 law 啊？不用紧啊，那个反正 physics 吧，
不需要看就是上课
啊，不能再 prove 的那种，我想想。哎，等一下，大家，所以那个 revision class 哦，好像是不可以放在考试周，如果放回去 revision week 那一周诶，所以拜早上啊，哦，同个这个时间，像拜五早上哦，10点到12点，还是我们早一点啊？什么？
这里没有把握，我记得啊，你讲这个时间这些不行。
10点到12点。
这个水我给你还有一个吗
OK
？OK。
10点到12点了。OK。OK，我再 reply 一下。About the publishing, I put a published version, right? Those that I put it up for you to study on is those that I think there's no major problem already. So you can read it. So you can try and learn from them. Okay. For those I didn't publish, you can try and work harder to like do editing. At most 2 points I can give up to you based on your correction. Yeah.
That's all. And make sure you know what I want from you. Because if you do something that I don't want, then I cannot give you mark. This is what happens in real life. When we write paper, also like that. When we write paper, we pass to editor edit. They will give you comment and ask you to change this, change that, or ask you what happened here. Then you need to explain. Yeah, you need to do what they want to do. Okay, yeah. So this is kind of standard thing happen in academia. Academia.
相关列出来。
我知道你讲什么，我就说那个是 physics law 不用紧。Yeah， 且你也没有 proof 它嘛，对不对？对啊，就不用紧。All right, let's continue with last theorem here, divergence theorem. Okay, so what's divergence theorem here? So, I mean, let's teach you some technical thing first, and then we'll tell you what's the motivation behind. Well, the first thing is Stoke theorem relate one-dimensional integral, I mean line integral to surface integral. But now we relate surface integral to triple integral here. Okay. Going up dimensional, one relate one integral to two integral. Now we are relating two integral to three integral. Okay, triple integral, double integral to triple integral. But what's the connection here? So in one dimensional, I mean going from line integral to surface integral, you need a closed loop that bound a surface. In here is the same. You need a closed surface that bound a solid. Okay, for example, you have a sphere. It's a closed surface. It bound a solid inside, which is a ball. Okay. And in the one, I mean, Stoke's theorem, you talk about the orientation on your what? Your curve, closed curve. Similarly, here we need to talk about the orientation on your closed surface here. Okay, so what's the orientation we get here is also a positive orientation. So in this case here, what's the positive orientation? Is the orientation that going upward. Okay, like a durian here. So what is it? So if you have a solid, okay, if you have a simple solid region, then you can find a bounding surface here. Okay, for example, what's the bounding surface for the Earth? Okay, it's a sphere. Okay, so a bounding surface of the Earth is a sphere. So inside the Earth, we have Earth core, right? Okay, so it's solid. And then you want to try integrate, okay, a vector field, okay, along this surface here, So it's equal to what? It's equal to the triple integral over that solid of divergence of F here. Okay, so if you look at it here, what do you see here? So this is really a triple integral of a scalar field. But on the other side, we have a double integral of a vector field. Okay. So what do you imagine here? So on this side here, the orientation is going upward. So if you imagine this integral is positive, meaning what? Meaning the integral of this divergence is also positive. So that's why we call this df as df. Okay. So it means how much you're going upward. Because if you imagine what happened here, you need to take your f dot with the outward normal vector. So that's why we call this this fellow that we integrate over df. Conservatism. 你可以 treat as 这个 df 是一个 scalar field 罢了，不知道什么来的。But integral of this df here match up with this double integral. Okay, but what does this double integral do? You need to take your vector field dot with the outward normal vector. 懂什么意思吗？ outward normal vector 啊outward normal vector of your boundary surface. OK 吗？我来讲，我在解释这个 df 的名字从哪里来。我可以叫它其他东西的嘛，这个东西对不对？我要叫它其他名。为什么选 divergence of that? This is because of the left hand side here. How we compute this integral? 我们这边左边是怎样 compute 的 ？We need to take the vector field dot with the outward normal vector of the surface. 我那个 normal vector 已经来规定了你这个 vector 来往外的一些 property. Okay, that's why we call it divergence here. 明白吗？就是一个 same example， 就是 same example here。怎么我们叫这个 Stoke Theorem 里面这个叫 curve f 啊？怎么叫 curve f？ 因为左边这个在做什么功？绕圈圈的工作啊，在绕圈圈啊，左边。左这边的东西就是看这个 vector 到底有没有在绕圈圈。Is the vector field curling here? Okay. Because on the right hand side here, you integrate over closed loop. 你要做功的话，你要绕着那个圈走。Understand? Okay, so that's why left hand side, the thing that we integrate over, we call it curl f. Whether this vector field is curling or not. Okay. 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 So this is a intuition how to think about this definition. So let's try one example then. Let's verify this. Okay, let's verify this. So let's verify this Gauss theorem. Okay. So let's verify this Gauss theorem here. So we have surface again, a paraboloid. Okay, but this paraboloid is in the other direction. Okay, it's in the other direction, just not upward, right? Now downward. Okay. And then how to describe this paraboloid here? Z is less than or equals to 1 minus x squared minus y squared. And then everything above 0. And then bottom here, there's a surface. Be careful. So there's a surface here, x squared plus y squared less than or equals to 1. Okay, so there are two ways to compute this number here. So if we do the bounding surface here, we need to try and parameterize x1 and s2. So how to parameterize x1 and s2 here? Okay. So x1 is given by this paraboloid in the negative direction. So 1 minus x squared minus y squared. So how to parameterize this? Well, this surface already tell you what's the z coordinate, which is z minus x squared minus y squared. But what is the x and y coordinate? What should we put here? What should we put here? X and y should be linearly independent. Okay, so you just put xy here. But what are the xy that you consider? Do you consider every xy or not? you consider xy in R2? Every xy? You consider every xy? What kind of xy you consider here? Only those that satisfy s squared plus y squared less than equals to 1. Okay, meaning only this with radius 1. Okay, all these as 1. Well, I mean, you can change these to polar coordinate, right? Because if you change it to polar coordinate, this is just a polar rectangle. Okay, if you do a calculation of polar rectangle, it's always easier, right? If you do calculation on rectangle in general, I mean. Okay. How about the second second surface here? How about this second surface here? How do you parameterize this second surface? X squared plus y squared less than or equal to 1. How to parameterize this surface? What's the z component? What's the z component here? And this surface here, the z satisfy what? 0. Okay, so the z component is 0. Then what do you put for x and y? Huh? If I put xy, you agree or not? You put xy. But the question is, do you take all xy? No, right? So what kind of xy you take? You only take xy such that x squared plus y squared is less than or equals to. So meaning you just take everything inside this with radius. Okay. So let's do this surface integral now. So let's do the surface integral. So what's this boundary here? This boundary is a union of x1 and x2. And it is linear. Okay, so you also have linearity here. So you can split this integral up to a surface integral of x1 and x2. So if you do this surface integral here, what do you get? There are two things to get here, right? So let's see what happened. So how do you get this two? So you should transform it to, first of all, transform it to D1. Second one, you transform it to D2. Okay. And then your vector field here, y, x, and z. So in this case here, you should put D1, you have y. Sorry. Yeah. Minus x squared minus y squared. Let's dot with what? There's a lot of things you need to compute here, huh? Should you compute it? What's the thing you need to put here? And what do you need to put here? R1. Yeah, so maybe how to put vectorly? Okay, maybe just like this. So R1x cross R1y. Okay, so have you computed? Let us compute it. So what is R1x here? Should be 1, 0, minus 2x. And then R1y should be 0, 1, and negative 2y. So if you dot these two together, you know what to get here? You should get 2x, 2y, and 1. Okay. Check. Okay. Maybe in this case here, you need to be worried a bit already, because whether you match up this outward normal vector or not. Okay, does it match or not? If you put 2x, 2y, 1, is it going upward? Going outward. Well, I mean 2x, 2y is just the same direction with your point, right? And then 1 is pointing up. So it's okay. Okay. How about the second one? What was the second one? Second one. So this is the technical part for computing this divergence theorem. You need to make sure your orientation is going upward. So what is R2x? 1, 0, 0. And then R2y is 0, 1, 0. Okay. In this case, what is R2x cross R2y? 都是出东西嘛。There's only one non-zero term, right? Which is k. Okay. So 0, 0 minus 1. 1. But 1, what happened to 1? Meaning what? You are pointing upward. But just now we say what? The surface have to have positive orientation, meaning have to point upward. Okay. So instead of taking R2x cross R2y here, you should take negative of it. Okay, you should take negative of it. So what do you left with? Left with y, x, and 0 dot with 0, 0, negative 1. Okay, you need to consider negative. Okay, ma? Because, I mean, if you take normal vector, right, there are two choices, whether you get the positive going up or going down. In this case, you get the one that's going up. But in this calculation, you need positive orientation. So you need to go down. So you need to manually add the negative. Okay. 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 Yeah. 对 ，then 就是要算这个。要算这个。所以你要算到它的答案是什么？那你算什么答案？它有算一个 version of 答案。我们没有算呀。我们要算这个。你们要给他们进来吗？进来不可以抄他们讲。大家你们进来不可以抄。OK， 算完这个，算完它，来算一下。安静。OK， 来算完这个。就 this。来算一算，给你2分钟。对，算完这个算完 divergence 我们才可以放学。算出来。 If you notice, one of the integral is 0, right? The second integral is 0. Because the dot product is 0. So you left with the first integral here. So the first integral here should reduce to 2xy plus 2xy plus 1 minus x squared minus y squared. But you see, this is kind of a tedious, I mean, troublesome, right, in xy. But you can do polar coordinate. Okay, let's compute it in terms of polar coordinate here. So if we turn it into polar coordinate, our integral domain become easy. Okay, so we just integrate with respect to dr d theta, where r is going from 0 to 1, theta going from 0 to 2 pi. So if you set the change of variable, you should get 4r squared cos theta sine theta plus 1 minus r squared. So don't remember, blah. So you have to remember there's a Jacobian factor here. Right, so there's a Jacobian factor r here. Yes. Must remember, if you don't remember, then you will have wrong answer. Okay, so there's an extra r here. Okay, then you do integration. Okay, if you do integration, you should get pi over the x. Okay. I think quite straightforward because once we do this polar coordinate, just integrate over r first. So this cos sine theta, yeah. So you need to introduce a double angle formula here to help you. So you need a double angle formula here. That is cos theta sine theta equals to sine 2 theta over 2. Okay, so let's look at the other side of this integral here. I mean, the other side of this equation. Let's see. So well, I mean, if we want to compute the triple integral of the divergence of f, so well, we need to compute what is divergence of f first. So what's the divergence of f? It's a gradient vector dot with your vector field. Okay, so let's see. What's your vector field? What's your vector field? Y minus x and z. Okay. So you can see that what's left here, that is just 1. That is just 1. So actually you are integrating over a 1 scalar field, constant 1 scalar. So what this says, this is actually a volume, right? Volume of your domain that you integrate over. But what's this E here? How do we describe this E? What's this solid we have here? What's the set we look at here? X, Y, Z in R3 such that what? X squared plus Y squared is less than or equal to 1 and Z is in between 0 and 1 minus X squared minus Y squared. Okay. Well, I mean, you can do this XY coordinate if you like, or we can transform this. Let's say if we want to transform this, which coordinate is better? Spherical or cylindrical? Cylindrical. Okay, we can try cylindrical. So cylindrical is R, theta, and Z. So meaning for cylindrical, meaning what? We just really transform the first R2. Okay, the first 2 coordinate. Okay, the third one we keep it. So if we do this, what happened? we were integrating radius from 0 to 1, and then theta from 0 to 2 pi. And also the height. What happened to the height? The height we just integrate from 0 to 1 minus r squared. Okay, because we already do change of variable here. S squared plus y squared equals to r squared. Okay, so in this case, let's do it in dz dr d theta form. Because what? Because our z is depend on r squared, but our theta doesn't depend on r. Where should my r go? My r should go from 0 to 1. And then there's also a factor here. Okay, so the factor coming from cylindrical coordinate is just r. Okay, so integrate this. So if you try and integrate this, let's quickly do it. We should get r times 1 minus r squared dr d theta. And if you integrate this, you will get 2 pi of r squared over 2 minus r to the power 4. 0 to 1. So I do it in one go because we can split it right as a product. Okay, iterated integral. Then we also get pi over 2 here. Okay, we get the same answer here. Yeah, so so for the last chapter here, right, what we really learn is how to relate triple integral with double integral, or double integral with just integral. Okay, integral line integral. And then after that, what you need to compute here, what you need to how to do these multiple integral is what we learned in the previous chapter. Okay, yeah. So the main thing in vectors calculus is how to do integral using parametrized curve or parametrized surface. Any question or not? There's a lot of example in your lecture now. Make sure please go back and do it, and then we can discuss again during the revision call. Okay. Any question before we take a break? Finish up. Anything about your assignment or report you're not sure what to do to them? Okay. Okay, if like that, then maybe we can take a class photo before we dismiss for the semester. Huh? Yeah. Okay, maybe we can take a group photo. So, 金生你觉得要怎样？站着还是坐着？坐着。摄影师200。OK。摄影师啊，摄影师。坐着，要怎样做？就这样子做。有点难，可能要去一边，去中间。OK， 去中间。Can you guys move your chair a meter to the photo?
怎么那么安静
啊？
班怎么那么安静？不用你那个黑色的纸，纸还是黑色的背景。
来 ，let's move to the middle. No need to bring table, bring chair in. Yeah, move to the middle. Okay, take a group photo.
会入镜。
你干嘛要入镜？
填了我的。
要做嘛，做完站。一些做一张，人讲做2张。哦，那边做，然后来全部在那个后面。坐落，然后全部站在他们后面，围着那一桌，应该就围着那一桌。对，呀，围着那一桌。
那个吵架。
近一点，左右近一点，左右近一点。 高的站前面呢，更高的站后面。
哟，谁人？
夹那边左边右边差不多在哪里？喂，看一下，左边跟右边。不知道。小杨进到后面，呀，对，没有错。还有谁？对呀，这样子。一想，对，一想要进到那个，再进来，对，你们还要再近一点，对。这边不好，我这边进来。绕这进来。那里面不会来。因为相机里面没有死。就是零啊。Okay, so please try exercise and then we will see you. Oh, then if you still have report, I'm sure you can say that.
可以等我一下，
等
我一下。
你吊起来找什么东西哦？
这样你不就是在做 quotient
等我一下。